Embedded Linux, Michael. So I think the first question, maybe to clarify, just to really set a baseline for everything, what is the difference between Linux and embedded Linux?
Hey, I'd say it's Linux, still Linux, but with with a reduced set of components and configured in a custom way. So using this definition, well, Raspberry Pi OS is not embedded Linux because it's like a standard desktop kind of OS, and Android would be, which is a bit weird, but and also embedded Linux is Linux when you don't recognize it, when it's hidden on a system, like it's working behind the scenes. And what I like about embedded Linux is that you've got a chance to really customize it and understand what's going on and really understand what you're doing. That's great compared to trying to understand what a desktop is doing.
Exactly. That sounds like one of the challenges of every embedded engineer, to be honest.
Correct.
So what is the state? As I was introducing there, sort of embedded Linux sort of came about around the same time as Linux really started to gain in popularity. So what's the state of embedded Linux for users today? And if someone had been using embedded Linux, let's say 10 years ago, what things have changed since then?
So I think about the state, Linux is, as you said, is really everywhere, including in space or on Mars. It's flying on the helicopter on Mars. And so embedded Linux succeeded where it failed on the desktop, unfortunately. Well, it hasn't succeeded yet, let's say. I had a look at what's new, like, since 2012, and my first answer was not so many things have changed. We're still using the same commands, same kernel, same tools. But actually, no, there were substantial changes in the last 10 years. So there's a quick list here that I prepared. There's cheap and powerful hardware. And indeed, in 2012, if I remember correctly, the Raspberry Pi was out. Before that, you had the Beaglebones and Beagleboard. But that's really when the cheap hardware was getting to be massively available. You've got also a new hardware platform. I'm thinking about RISC-V, which is an open source instruction set with that is royalty free, unlike what you have on ARM. And you can really design now completely open source hardware, including the SoC. So there are some SoC projects you can use. You can actually flash them on FPGAs and have a completely open source hardware design now. So open source chips are coming as well. Well, proprietary as well, of course, but open source ones as well. So that's interesting. Something new too is the Clang C compiler from LLVM. It can compile like most things now. Like with Yocto, with MetaClang, you can compile the whole stack with Clang instead of GCC. And now Clang can also build the kernel, the Linux kernel with GCC as well, which is something completely new. And that's a nice achievement that was a nice driver for improving Clang as well.
Right.
Don't forget Rust as well. It's getting popularity. It's starting to displace C for system applications. Many people are talking about Rust instead of C programming. So that's at last something interesting. Other things I could say is that we've seen more exposure to security vulnerabilities. Like, it's not like Linux is less secure than before, but there's more attack surface, more devices are connected, and then there's a strong focus on the kernel side to find bugs and to fix them and to reduce the attack surface or to implement things that make it harder to break into a Linux system. But since Linux is a moving target, changing all the time, how can you make it super secure? It's impossible. Yeah. So that's always a trade-off. There's something new. There's VS Code from Microsoft, Visual Studio Code. As a surprise, I mean, I would have never said 10 years ago that I would be talking about a tool from Microsoft, but it's open source and actually doing pretty well. And Microsoft has changed as well.
I was really surprised, actually. I was looking through some forums for text editors and development environments, and I was surprised how many people suggested VS Code actually for Linux systems. So,
correct. And by the way, Microsoft doesn't seem to belong to the bad guys anymore. They are part of the Linux Foundation. They support nice open source projects. So they have gone a revolution internally. That's also a nice paradigm shift as well. Other than that, in the list I have, I see open source GPU drivers have like, they were like in their infancy, or if not existing yet 10 years back, and now they really start to be usable even in desktop distributions, and that's really makes the life of our customers so much easier.
What was the challenge around the GPU drivers? Why have they been sort of closed source for so long?
I guess it's where the GPU makers are coming from. They have like they need a huge blob of software to run their GPUs, to implement OpenGL and things like that. So traditionally they had the same mindset as TI had it at the beginning. Like they were like super focused on their intellectual property and not wanting to open it at all. And then they really evolved. And I guess those guys, well, it's not completely true, because some of them are still like with the original mindset, but the community has gone a very long way as well. So like showing the vendors that they can really achieve great things and implement functionality that even match or exceed what the proprietary implementations can do. So that kind of influenced the SoC makers as well, the GPU makers.
Wow. Yeah. Fascinating.
Yeah.
So one of the questions that I had on my list was the challenges that sort of beginners have. Sorry. It's a long list.
yeah, it was so long, so I didn't want to miss anything. Maybe people remember the code sorcery toolchains to cross-compile your software. Code sorcery is gone. They've been sold to Mentor Graphics, and then they don't release interesting open source toolchains anymore. So we have like worked on the replacement. So if you go to toolchains.bootlin.com, you can find like toolchains, GCC toolchains for many architectures, many versions of GCC, and we really intend to make that like available for forever if possible. So that's good, useful resource, I think. There's also the binary reproducibility efforts. At least in the Elektor project, for example, when you generate two file systems from the same configuration, it's going to be the same at every bit will be the same. And if you make a change, just the bits that you change will differ. That's together with the reproducible bit projects, and really that helps with validation and things like that. You're sure that you don't add backdoors when you generate a new binary. Like if the binary was completely different, how can you make sure that there was no evil thing added to the image?
Exactly. Yeah.
Also thinking about the Barebox bootloader, which came out as a nice alternative to U-boot. So check it out. It's not like it doesn't have the critical mass as U-boot does, but it's really interesting. Something great too is the Linux kernel long-term support releases, which are provided by the community like for almost 10 years, and that's the only way you can have a secure kernel for a long time.
Exactly.
Unless you work with the commercial embedded providers such as WinRiver or Timestes, they have a team to do that, but internally you can never match this. It's too much work.
Exactly. Yeah.
And the last two things I wanted to mention is it's now easy to support a new board with the Linux kernel. Just tweak a device tree and you're ready to go. This was just starting 12 years ago.
Right.
And there's also a nice tool for building your packages, and that's nice for build systems as well. It's the Meson together with the Ninja that replace Make and the AutoTools and Make.
Yeah. I think most people would appreciate that. I've always struggled with Make and Make files.
Oh yes, that's such a nice
messy.
Thing. May I say a few words about Bootlin and the Elektor project, maybe?
Yeah.
Quick words about Bootlin, just to say. So I belong to an engineering company. We do mostly low-level stuff related to embedded work. So bootloader, kernel work, integration, like build systems. So all the low-level stuff to help people get their hardware working on with embedded Linux, right? And we are happy, really proud to have contributed to interesting bits in things like Linux, like we maintain a few ARM sub-architectures, and also in the bootloaders, in Buildroot, in Yocto. So it's really great to be there and be part of community development. And we also have at Bootlin, for those who are interested in learning, we have courses about various topics related to embedded Linux. And all the documents are available on the free documentation license, like the Wikipedia content. So don't hesitate to go and go there and learn. It's really meant for people to be used by people who want to learn by themselves.
Super. And that leads us well into to my next question, because I remember when I attended your course 15 years ago now, I think it was. Yeah, exactly. I mean, there's so many components to embedded Linux. I remember going to one customer with, we were working on that DaVinci device, which is that C6000 core and very much focused on video. And one of the questions that came up was, how can we make the bootloader faster so that we can have some sort of splash screen as quickly as possible when our product is turned on? And as you sort of delve into embedded Linux, you realize there's just so many pieces. I mean, having trained so many people and seen so many people entering embedded Linux for the first time, what are the things that people have most challenge with when they're getting started?
Oh yes, so I've got a slide on that because you warned me. Yes, when you want to get started, what they struggled with. So maybe I can start with this and then answer your question. Yeah, to get started, my advice would be to start small. Like, don't try to build a complex system. Just pick up some nice hardware, like the Raspberry Pi, if you can buy one. If you win one today.
You never know.
Yeah, or a Beaglebone, or the hardware from Olimex, which is open source hardware, or from Supercomputers, nice people too, or just QEMU. QEMU is nice and can emulate a bunch of ARM and RISC-V boards typically. Then just compile a bootloader and kernel for this emulated or this architecture, and just flash a simple file system with VisiBox. So just simple command line utilities that are super easy to compile. Just flash them on a drive and boot your device with that. And then you can see how simple things are. And then you can grow in complexity and add more things. But Linux can be super simple. You just need 3 components, like the bootloader, the kernel, and VisiBox. That's a user space program. So in case you're interested, I made a presentation. You have the references on the screen. Yeah. Like last year at FOSDEM, just how to have a working embedded Linux system based on RISC-V in 45 minutes. Wow. Everything is compiled from scratch in 45 minutes, and you can really understand how it works. You have a web interface with this. So that's one way to go. Start small. That's my best idea. And then, of course, the challenges people face would probably that there are too many ready-made solutions on the internet. Already, you could be drowned and not really figure out what to choose. There are so many resources out there, so many components. But so please start simple. Don't get you overwhelmed by the complexity and all the possibilities. Really go little by little and take the time to understand what you do. That's the best advice I would give. And that's exactly what my friend Josef Olsenmeyers said in this nice presentation that I referred to here. 5 typical mistakes that people would make when they start with embedded Linux, like getting some code they don't understand, or some solutions from Stack Overflow, and go ahead and do things, and then they have the impression they save time, but in the mid and long runs, they waste a lot of time by not doing things right because they don't understand what they do. Yeah. So that's a good idea to watch this video as well if you're interested.
And for those examples that you gave in terms of getting started and bringing up a board, do I actually have to also run Linux on my development PC as well, or are there ways of doing it from a Windows PC?
That's that's recommended to use Linux as an environment for building all this, because otherwise it's complicated. You'll be the only one doing that. So at least use a virtual machine. Yeah. With Linux on it. That's easy with solutions like VMware or VirtualBox. The VirtualBox is open source,
Yeah.
so that's really pretty easy to do. And this way you have the same environment as the rest of the community. In case you have trouble, you can report your issues, and people will help you because they work in a similar environment. So definitely advisable to start with Linux on at least on a VM for this purpose. But it's fine to keep Windows for the moment.
Now, as you said earlier, sort of developing any sort of application is relatively easy for Linux. You have a C compiler there, you can write some C code and have something up and running, and there's all that support for networking, for file systems. But I think one of the sort of the bigger challenges is when you've got some hardware and you want to use some peripheral on that SoC that hasn't been supported yet. So when you need to get support for bare metal features and develop a driver, what's the process for developing a driver, and how do you test it? How do you then make sure it's sort of efficient within the Linux environment?
Okay. Well, you have two ways of doing that. You could like driving hardware. You could do it the Raspberry Pi way, like you've got Python classes for lots of sensors, and they probably are quick solutions that work well, right? But the thing is, each one comes with their own API and on their own way of providing the data from the sensor, from the device, and ultimately you'll find out this is not portable at all. Like every time you change the sensor, you're going to work probably with a different library, and you have to adapt your application. So ultimately, it's effectively a good idea, as you suggested, to work with a kernel driver, a solution in the kernel. So it's possible to drive things from user space, but it's more efficient and more portable, and more reusable to write device drivers. So to write device drivers is not so complicated. You could check our courses on kernel development. You can start by studying existing code, and so like with a simple I2C device, for example, that's a good way to start. And you see how this all fits together, how the kernel recognizes the device, how you can within one driver support multiple devices, and then progressively, it's effectively the next good thing to do is to start working with the community, to show your driver to the community and say, what do you think? That's my first driver. Please be
please be nice.
Please be nice. Yes, please understand. But what do you think? Would you be interested if I share it with the community? And then you have great feedback from people who have a lot of experience and also have an interest in supporting you, because ultimately your driver could be in the kernel that everyone uses. So that's progressively, if you get involved like that, it's great. Plus you have great tools for Linux kernel developers, for testing, for finding regressions. People will also help you maintaining your code. So I think that's the way to go, progressively get closer to the mainline kernel community and work with them to get your code adapted as well. And that's a great way of learning.
Super. So embedded as a term is closely associated with real-time applications, but Linux is a big operating system. It's not the same as something like FreeRTOS or some of the other sort of bare metal OSs that are out there.
I agree.
How real-time is embedded Linux today, and what sort of knobs do I have available to me to turn in order to improve the performance of Linux for real-time applications?
Well, Linux is definitely a big beast. Like the scheduler is super complicated, so you can't really make it like super deterministic. And determinism is really what we care about when we talk about real-time. You want to guarantee response time within a given amount of time. So performance is exactly what we're looking for, but rather determinism. So, but fortunately, the kernel developers have worked for years in trying to identify the biggest sources of non-determinism in the Linux kernel. And I can have a slide about that. Yep, that's the preempt-RT patchset. So it's eliminating the sources of non-determinism in the kernel. This had started like almost 2004, I think. And so that used to be a quite big patchset, and now the effort is starting to pay off, and they're getting close to having all the features in the mainline kernel, which means you won't need the patch anymore,
Right.
like with 1 year, hopefully, something like that. So with this, you can make tests, but like for example, on the Beaglebone, you can guarantee that your reaction time will always be within 70 microseconds or something like that. So
Wow.
that's pretty good, I would say.
Yeah, yeah.
I mean, hopefully that's enough for your system. And yes, you've got this max response time to react to an event like an interrupt or things like that. That's the worst case, like when you start reacting to the event. This being said, so the infrastructure is getting much better now, and you could
Yeah.
use it. You could use other projects that are even better but more complicated, like Xenomai. Xenomai adds a real-time kernel between Linux and your hardware, so that
Yeah.
the real-time applications are really handled by a real-time scheduler. So like you can divide the reaction time by the worst case reaction time by 3 or 4,
Right.
but it's more complicated to support. Not all hardware is supported. So that's what. So these are the low level solutions. But on top of that, of course, it's not because Linux is real time that everything is easy. You still have like to design your system correctly, allocate resources ahead of time before your system goes real time. You also have to set the priorities properly, and so you have to do your homework, like system design work, proper system design work, to get the right things done. Otherwise, the Linux kernel won't know what to do, won't know what's important.
Exactly.
So yeah, it's pretty good, I think. Elon Musk says that they're running preempt-RT on the Starlink satellites, at least.
Oh, really? Okay.
Yeah, and since then we had like more requests for preempt-RT. I mean, it has increased the popularity according to everything that Elon Musk says. They're also running some Linux, but I'm not sure whether it's preempt-RT on their on the SpaceX launchers as well. So that's a surprise. But I would expect VxWorks or the other one on those systems. But ultimately, they even have used this one.
Okay.
Amazing.
Super. So, there's so many questions to ask, and time's going by very quickly. So
we
just
can have a number 11 if you want.
Exactly. So just to play one more question while we're in a one-on-one session. You're deeply involved in the Octo project. Could you just explain what is the Octo project and how does it differentiate from other competing embedded Linux distributions that are out there?
Yeah, okay, sure. So the Elektor project is a collaboration project that's now hosted by the Linux Foundation, and essentially it's a way to generate distributions, embedded Linux distributions, custom ones, and it's based on the open embedded build systems that has been around for like 10, 20 years now. But like it's really the Elektor project is under the Linux Foundation umbrella, gathering some member companies and really supplying some good resources to drive the project, to support the project. So what's interesting in the Elektor project is that the build system is extremely flexible, powerful, and can really be customized as much as you want. For example, as I said, you can build the entire file system with Clang, for example, just by adding a special layer that's called MetaClang. So that's impressive. And yeah, you can tweak really everything and really leverage the prior work of hundreds of embedded developers who have put their knowledge about building components in recipes, and so lots of components are available. There's a great community as well. Like if you want to join, it's really really nice. We're really welcoming people. This kind of project makes you feel like contributing to it. It's really nice, and it's really well supported by the big SoC vendors as well. Like they provide their own layers for compiling their kernels, for supporting their hardware. So you've got everything you want. The difference maybe with others is that effectively it's super smart. Like it rebuilds only what needs rebuilding. It may be too smart, so there's a learning curve to this.
Right. Okay.
Right? And if you compare to Beetroot, for example, Beetroot is much easier to get started with, but it's not as versatile as the Elektor project is. So that's still a very good, worthwhile investment to to try this one.
Yeah.
I would say.
Super.
By the way, yes, I saw last week a coffee machine based on Yocto. That was great.
Yes, I saw that. Yes, you wrote about it. Yeah,
that's right. So that's awesome, and there's endless things you can do with that.
Exactly. It's always a good feeling to see your code out in the wild, isn't it? Super. Well, thank you very much for all of those insights. We're just going to leave it there for a second before I bring in Ricardo to talk about containers. So stay in the line, and we'll bring you back at the end for the question and answer session. Thanks very much, Michael.
Thanks, Stuart. Thank you, everyone.